Planck's wave and de Broglie's group. Here's the quantum. The quantum is a wave-particle duality. The wave is Euler's wave. It's an infinite wave. And the particle is localized on the normal distribution. The wave is derived from Maxwell's equations with the electric field in the vertical plane, the magnetic field in a horizontal plane. They're out of phase by 90 degrees. And they have two velocities, a group velocity and a phase velocity. In light, the two velocities are equal, but in mass they're different. And that's the topic of this presentation. And the uncertainty is roughly the full width of maximum, but precisely we make that point equal to 1. And the normal distribution, we decides the uncertainty. We take this equation, choose k and x to be 0, and we make tau at this point the uncertainty in time. And we introduce this value of 1 into this equation and find the uncertainty in time is 2 sigma over mean omega. Very simple. That's the uncertainty in time. And what about the uncertainty in angular frequency? Well, the transform of a Gaussian is Gaussian, and the wave function as a function of omega is given here by the Fourier transform. And when we do the same procedure as we did before, the uncertainty in angular frequency is 4 omega over sigma. And the physical constants cancel out, and the dual uncertainty is equal to 8 as a number. And likewise in space, dk sub x is equal to 8. And that's a most probable uncertainty. It's not a limit like Heisenberg's limits. And we've experimented on this with electrons. This is an electron passing through a slip, shows the wave function. And if you think of this as a limit, like Heisenberg's limits, whatever that is, then this limit depends on the extremum of Cornu's spiral, and is 4 times greater than Heisenberg's limit. Well, that's one kind of limit. The limit depends on the wave function, and it depends on the experimental environment. We don't have any absolute limits. Well, we've done the quantum, we've done uncertainty. Let's do de Broglie's discrepancy. In classical mechanics, momentum is mass times velocity, and kinetic energy is half mv squared. In classical wave mechanics, the velocity is the frequency times the wavelength, that is, the number of wavelengths that pass a point in a given time. And it's, by definition, equal to omega divided by k, the angular frequency divided by the wave vector. Now, if you substitute this velocity into here, what do you get? The momentum is mass times frequency times wavelength. Hello? That's opposite to what de Broglie had. And what's the reason? Well, you can guess. The reason is those two velocities, and we're now going to sort them out with relativity. Einstein knew that the speed of light is the same in all directions and deduced that the physical laws are invariant in all inertial reference systems. And he showed that energy is mc squared. Oh, this is relativistic mass. In Einstein's dynamics, mass changes, not in Newton's dynamics. In Newton's dynamics, mass is the rest mass. We're going to see what the implications are for that change in mass. And Einstein found that the energy is due to 2 factors, the rest mass and the momentum. Now, Planck's law is quite easy because the energy is proportional to the angular frequency, it's proportional to the velocity, and it's easier to accept this law. But what about momentum? We just found a discrepancy. How do we find the true momentum in terms of the dispersion dynamics? Well, we convert this equation into dispersion dynamics using the conventional formula. Omega squared is k squared plus m squared, plus including some constants. Differentiate through this equation, and you find omega over k multiplied by the derivative d omega by dk is c squared. What's omega over k? We found that before. That's the phase velocity. That's no problem. What's d omega by dk? Well, we're going to find out by more than one argument what d omega by dk is. First of all, go back to Newton's dynamics and notice that momentum is velocity times mass. That's the group velocity times mass. Here it is. It's equal to p squared over E0. And if you do look for the same equation in relativity, just notice a few things. The way you relativize Newton's dynamics is to swap E for E0. Newton's laws are not wrong. They're just only approximate, and they approximate only where the energy is low, and incidentally the velocity is low and mass is low. But when we look at this equation, we find that the group velocity, translating E0 to E to make it relativistic, is equal to, with a little bit of substitution, V is equal to d omega by dk. That's what we said. So we come back, the group velocity times the phase velocity is equal to c squared. The group velocity is the inverse of the phase velocity. And I can give you a physical argument to back that up. Think of a piano tuner. One string is out of pitch. And what the piano tuner hears is a dominant wave which modulates, it beats. And it beats with this, at this wave beat. And just as the velocity of the carrier wave is omega over k, as we just showed, the velocity of the beat is d omega by dk. And when you integrate that over the normal distribution, it's the derivative, which now is the property of relativity. And here we get the group velocity times the phase velocity is c squared. That is a fact that has been overlooked in modern physics. Let's draw them out. Here's the rest mass of Newton. And in relativity, the mass increases with increasing k, increasing energy. And the velocity and kinetic energy start at 0 and increase equals half mv squared. But in relativity, that velocity tends to c at high k, at high energy. And the energy is going not into velocity, it's going into mass. That's a fact of relativity, which we're now going to take full account of, because it tells you what mass is. And notice also, when you have a particle that is massless, the photon, Vg equals Vc, and the energy is proportional to the momentum. So this ratio is telling us what momentum, what mass is. And it comes in two parts. In the first part, rest mass, where Vg is 0, the rest mass is due to the phase velocity, the internal motion of the particle at rest. And when you increase the energy, you increase the mass, and the increase depends on the group velocity, not the phase velocity. And they're exclusive. And this tells you a fundamental feature of mass. And now I'm going to ask another question. We've seen the wave particle. We've seen uncertainty. We've studied mass. We're going to display some of its other properties, not systematically for the moment, just how you do it. Here's the momentum, and here's the rest mass. It's 5-dimensional, 3 for the momentum, and these are 2 scalars. But we can represent them as spherical spheres, and this is a tangent point because of the Pythagoras' theorem. So we have momentum, rest mass, and energy is collinear with time. So you can do all sorts of things with this display. When you take a cut through this, a section through this diagram, 3-dimensional diagram, and this is a plane inside the cut. And with this you can describe energy bands, band gaps, and many other features, but I'm not going to go into that any further now. It's in the literature. But what I am going to do is ask you, what forms the quantum? What makes it a quantum? And what makes it disappear in collapse? Well, I'm going to illustrate that by describing not the energy momentum, but not the energy quantum, but the momentum quantum. And the momentum quantum as it appears in diffraction from crystals and quasicrystals. They're very different, and I'm going to show you some complication. In crystals it's easy. Periodic probe, periodic crystal, periodic diffraction pattern. A Bayes-Bragg's law, n lambda equals 2d sine theta, and is an integer, 0, 1, 2, 3, 4, 5, 6. This is the crystal, the quasicrystal is different. Periodic probe, hierarchic lattice, geometric diffraction pattern. How does that happen? We can do some elementary things first, which we have to do. Map on a stereogram the principal axes, here they are. And normal to the principal axes are principal diffraction planes. And they're all 3-dimensional, geometric, simple and complete. If you don't begin with the right indexation, you'll lead nowhere. And here's the geometric series, 0, 1 over tau, 1, tau, tau squared, tau cubed, tau to the 5th. Thoroughly geometric. And the first question is, how does it diffract? Here's a crystal, here's a quasicrystal. In crystals, at a Bragg condition, the interplanar spacings are unique and periodic. And the wavefront is conserved in the incident beam, in the transmitted beam, in the reflected beam. In quasicrystal, completely different. There are multiple interplanar spacings, and the wavefront is completely distorted. It should be like opaque glass, but it's not. How do we understand it? Well, there's only one way to understand it, and that is by calculating the structure factors. And that is how we got that, by calculating the diffraction structure factors. You can find that diffraction pattern that we started with. Those dots were due to parallel beam diffraction, a parallel beam in and a parallel beam out. Here's a convergent beam performed with electrons. And what happens is we converge the beam on the specimen, and then each dot turns into a circle. And this is a strange set of circles. Here's the geometric pattern. 0, 1 over tau, 1, tau, tau squared, as we saw it before. But within this pattern is another pattern. 1, 2, 3, 4, linear. 1, 2, 3, 4, 5, 6, 7, 8. We've got two patterns. One is geometric and one is linear. And what are they due to? We know what Bragg diffraction is. We've worked out from structure factors what geometric diffractions. What are these diffraction patterns? And we get a sign from here. See these doubled up, and these are doubled up. That tells you these are dynamical diffraction. Dynamical diffraction occurs when two beams are strongly interacting. A zero-order beam interacts with a Bragg diffracted beam, and they swap energies like a pendulum, it's called, or like a bell ringing. And they swap energies here, they swap energies here. This swaps energies with this swaps energies with this. They're all dynamical diffraction. So here we have a very complicated system. It's much too complicated for mathematics. You can't make an axiom out of this. It's a wave and a particle. It's logarithmic and linear. It's natural and irrational. It's complex and imaginary. They're complex algebra with a new metric. This is a new metric in physics, copyrighted by the Smithsonian Astrophysics Data System, and it's the Log-Lin metric for generic responses in logarithmic structures. This is all very complicated. You can't make an axiom out of this. This is real physics that we have to understand. And so I come to my conclusion. You have to acknowledge now de Broglie's hypothesis works through group velocity, where Planck's and Einstein's quantum energies work by phase velocity. How can you resist the importance of internal motion? And this is justified by every electron microscope which knows what the wavelength and the frequency of its electrons are, and has many effects: impact parameters, intrinsic spin, five-dimensional electron-positron bands, superconductivity, low TC and high TC, multi-dual quanta in seabed, photoelectron reverberations at exaFs and exaFs, collapse of the wave functions, and on and on. This cannot be ignored any longer.